Okay, so let's talk polar bonds. Okay, we were just presented with the fact that oil and water don't mix, and the reason why oil and water don't mix because water is polar and oil is non-polar. Now those are polar molecules. So oil is not polar, water is polar. What does that mean? Well, before we can have a polar molecule, the first thing we have to talk about are polar bonds. All polar molecules have polar bonds. They also have a certain molecular geometry that allows for the molecule to be polar. So just because you have polar bonds doesn't mean you're going to have a polar molecule. And we'll talk about that coming up. But let's talk about what polar bonds are so we understand that first. So I'm going to go ahead and start here. And so, yeah, we're going to talk about polar bonds. Let's go on to it. In order to understand what polar bonds are, you have to understand electronegativity. Okay. And as it says right here, electronegativity, we learned this in chapter 6, is the ability of an element to draw electrons toward itself. Okay. And we have a number for electronegativity. It's a value. If you look on the periodic table, well, you look on a table like this, every element has an electronegativity to it. The highest electronegativity is 4.0 over here for fluorine, and the lowest is francium's over here, the zero point 0.7. Okay, so this is the highest, this is the lowest. We already saw that there is a trend, periodic trend, that increases electronegativity from left to right. We see that right here. And as you go down the chart, electronegativity decreases. So, really, what happens is when we form a covalent bond between two atoms, they're going to share electrons, but they don't share them equally. They share them unequally, depending on what the electronegativity is. And so, these elements over here in the upper right, let me try this, I think I like this better. These elements over here in the upper right, they have higher electronegativity. Think of them as like a stronger person, much more muscular. On the other hand, these guys over here on the left have lower electronegativity. They're really weak. And when there's a tug of war between the two, the stronger ones are going to pull the electrons closer to themselves than the less stronger ones. Okay. And we're going to get three types of bonds from this. We're going to get polar covalent bonds, is a covalent bond that is polar. A nonpolar covalent bond, which is a non-covalent bond that is nonpolar. And then there is the ionic bond, which we've already kind of talked about. The polar covalent bond is one that occurs when there is an electronegativity difference that is greater than zero point 0.5 between the two atoms, right? Between the two elements. So two atoms are different elements because if they're the same element, they're going to have the same electronegativity. But if they have two elements, two different electronegativities, if their electronegativity differs more than zero point 0.5, then that bond is going to be polar. What that means is that there's going to be more electrons pulled one side than the other. So between oxygen and hydrogen, excuse me, between oxygen and hydrogen, there's an electronegativity difference of 1.4 electronegativity units, right? Oxygen is 3.5, hydrogen is 2.1, so the difference is 1.4. That means these electrons that are shared between the oxygen and hydrogen are pulled closer to the oxygen than the hydrogen. There's an unequal electron density distribution. In other words, these electrons that are being shared between the oxygen and hydrogen will go over by hydrogen, but they spend more time over here by oxygen. And since they spend more time over here by oxygen than by hydrogen, it's almost like there's more negative charge on here than over here, giving this side of the molecule a partial negative charge. And we show the partial negative charge using this Greek letter. It looks like a little note sign, right? It's a Greek lowercase d. It's a delta. So this is a delta minus to show that there's a partial negative. It's not a full negative. It's not like a chloride ion or a bromide ion. It's a partial negative. And because the electrons are pulled in this direction, the other side of the bond and the atom on this side of the bond is hydrogen, has a partial positive. So there's a partial negative and here's a partial positive. So whenever these two atoms, when their electronegativity differs by by more than 0.5, it's a polar bond. And one side of the molecule or one side of the bond actually has a negative charge, the other one has a positive charge, a tiny one, a partial one. When two atoms are the same electronegativity, or when two atoms have very similar electronegativities, then there isn't a big difference in the ability to pull. They both pull equally, and the electrons are shared equally. That would make it a non-polar bond. Okay, so that's what would bring us back to here. We have non-polar covalent bond, and it's bond where there is less than 0.5 difference in electronegativity. Two atoms of the same element, they're the same element. They have the same electronegativity. Okay, if they're different elements, but their electronegativity differs by less than 0.5, then that's also nonpolar. The last one's the ionic bond. We've already seen it before, but what makes an ionic bond an ionic? Well, this one is a bond where the difference in electronegativity is greater than 2.0. Okay, so if if you look at back here, if you look at sodium chloride, sodium's 0.9, chlorine is 3.0. The difference between 3.0 and 0.9 is 2.1. Okay, that means that chlorine is so much stronger than sodium. It pulls the electron off and takes the electron as on its own. So now you get a chloride ion. So whenever one atom one element has two more electronegativity units than another element, then it pulls the electron completely off, forming a what do you call it? A ionic bond. Now those are just guidelines. The cutoff points are a little sketchy, but just to give you an idea what it is. Okay. So here are some more examples of a non-polar covalent, polar covalent, and ionic bond. So here you got two chlorines, and the electrons are shared equally. Here you've got a hydrogen and a chlorine, and the chlorine's 3.0, hydrogen's 2.1. The difference is 0.9 between these two, and so the chlorine shares the chlorine takes the electrons more. They're both sharing electrons still, but the chlorine spend more time. See how there's more of a bulbous end here, and there's less electron density here. That's what these are. They're electron densities. How much the electrons are, how much time the electrons are spending. The bigger the little round thing is there, the more time they're spending on that side. So there's the partial negative. There's that Greek delta again. There's a partial negative on this side and a partial positive on this side. And those positives and negatives are going to be important. Not as much as a full ion, but pretty much very, very similar. And we're going to see that in the next part of this when we talk about polar molecules. Once again, when sodium and chlorine get into a tussle over it, chlorine is just so much stronger than sodium, it pulls the electron off, forming a negative ion and a positive ion, because the difference between sodium and chlorine's electronegativities is greater than 2.0. So the chlorine pulls the electron completely off the sodium to form an ion. Okay, so let's take a look at these these polar molecules. How are polar bonds and polar molecules different? How are they related to each other? How are they different? All right, so we have one thing I hadn't mentioned yet so far is that when we have a polar bond, we create what's called a dipole moment. Basically, what a dipole moment is just a way of measuring this separation of charge. The bigger the separation of charge, the more positive and more negative it is, the bigger your dipole moment. And one thing I want to explain is that dipole moments, this is right here, dipole moment has a magnitude and a direction. In other words, there are things that are a little bit polar, more polar, and very polar, right? So it's not just a polar or non-polar, but we're basically going to be treating it as a polar, non-polar at this point in time. But there's levels of how polar something is, or polarity. It also has a direction, right? So this dipole moment right here is represented by this arrow, with a cross at the end, right? We draw an arrow and put a little cross at the end, and the cross represents the side that the of the molecule, or the side of the bond where there's a positive charge, the partial positive is there, and the arrow points in the direction of the partial negative. Okay, and that way, when we put together a whole molecule, or this is a whole molecule, but when there's bigger molecules, we can kind of see in which direction each dipole moment goes. Not only if there's a separation of charge, but in which direction it goes. Okay, so let's go ahead and take a look at molecules. So this one is a polar molecule, and we can tell it's a polar molecule because there's only one bond in it. And so if you can divide it so that one side of the molecule is positive and the other side is negative, that makes it a polar molecule. So not only do you have to have polar bonds, but those polar bonds have to create positives and negatives so that the molecule is broken up into a positive side and a negative side. So we're going to see a little more complex molecules in a little bit, but I'm starting off with HCl because it's kind of a relatively simple molecule. So it's easy to see it. We can represent, I'm going to go here. We can represent HCl as this molecule right here. Right? This little thing will represent the molecule. And this side's the hydrogen side because it's got the positive, and this side's the chlorine side. If I go back over here, you'll see that the partial positives on the hydrogen, the partial negatives on the chlorine. Another thing I could have done is wrote that arrow pointing this direction with a little plus on this end. That would also represent the polar bond. Okay. Now, since the whole molecule is just two atoms, we break it up into two sides. Now, let me explain something called dipole-dipole forces. Dipole-dipole forces is when you have what we call permanent dipoles in a molecule. And this is a permanent dipole. It's dipole because there's two poles, a positive pole and a negative pole. It's always a positive pole and a negative pole. So one side of the molecule has a positive charge, the other side has a negative. And remember, they're they're partial positives and partial negatives. They're not as strong of a positive and negative charge as on a positive ion or a negative ion. Okay. And so what happens with molecules that have dipoles is they start attracting each other. So one molecule that has a dipole is going to attract another molecule that's got another dipole. So let's go ahead and put this molecule up here. We'll bring in another HCl molecule, and that is going to line up so that the positive end of the new molecule lines up with the negative end of the other because they attract each other. All right, so now we're going to get these guys going. If you put a whole bunch of them together, which is normally the case when you never have one or two molecules, you have like gajillions of them at a time. So if you do that, they're all going to line up so that positives and negatives line up next to each other. They're all going to line up like this, okay? And so those are dipole-dipole forces. Not only is this negative next to this negative is also next to this positive down here, which is next to this negative, which is next to this positive, et cetera, and so on. It goes up and down as well as left and right. Okay? Those are dipole-dipole forces, and they are attracted. They're not as strong as a positive and negative ionic bond, like in sodium chloride, but they're strong enough to pull them together. Okay. These are not the only molecules that can form dipoles. Water is an example of a rather polar molecule. And that's because, remember, water has a bent planar molecular geometry. So we're going to have to take into account not only the polarity of the bonds in a molecule, but also the direction of the dipole moment. So there's a dipole moment between oxygen and, I'm going to draw this here. I think they showed right here, allowed to do this. There is a dipole that's going like this on this one. So now I think we can draw better with this tablet over here. And there is another dipole over here. So this one actually has two bonds that have dipoles, and you'll notice that both of them are kind of going up. Now, these dipoles have components. So this dipole, let's say a dipole going that direction, has a component going in this direction. In other words, it's going to the left. right? If I go ahead and drop this down here, it's going to the left, and it has a component going up. All right, so these things called vectors. And what we can do is we can break up this dipole into component dipoles. And what you'll see is that this dipole has these components. The other dipole over here has these components, right? It's going in the opposite direction. So this one right here, dipole B is over here. This was dipole A over here. This is getting the technical definition, but it's all right. And it can be broken up into these components, the component going in this direction and the component going in this direction. All right, so this dipole is made up of these two dipoles. And one thing you'll notice is that this one up here has a dipole going to the left. The other one has a dipole going to right. Those guys offset each other. All right, so they cancel each other out. On the other hand, there is another component going up. Both of them have it. So the resultant dipole of this water molecule is actually something like this. All right, so water is forming a dipole. Okay. That's, I know, kind of technical. That's basically the way that you figure out if a molecule has a dipole and therefore a molecule is polar. But that gets a little bit mathematical too. What I just try to tell people is if you can make this line right here that separates out a positive side of the molecule from the negative, right? This is positives, right? The hydrogens are positive. The oxygen is negative, right? I'm showing it here, but I'm making kind of a bigger thing of it. If we go ahead and we can divide the molecule into a negative side and a positive side, you have a polar molecule. Okay, so for that reason, I'm not going to test you on the polar molecules because it gets a little complex. Just know that a polar molecule is one where you can divide it into a positive side and a negative side. This one's easily obvious, right? You can separate out the positive side from the negative side here. Now let me contrast that with a nonpolar molecule, okay? A nonpolar molecule. Okay, so let's take a look at some nonpolar molecules. These both molecules are both nonpolar, but for different reasons. Cl2 is nonpolar because both atoms are the same element, thus they have the same electronegativity. So even though chlorine's rather polar, it is, not. This one is polar. Electronegative. So chlorine's pretty electronegative, but they're both chlorines, so there is no dipole moment between these guys. This is a nonpolar bond. If there are no polar bonds, the molecule is nonpolar. On the other hand, carbon dioxide is nonpolar for a different reason. Carbon dioxide has two polar bonds, slightly polar, but they're polar nonetheless. So between carbon and oxygen, oxygen is more electronegative, gets a partial negative. Carbon gets a partial positive. Same thing between the bond here between these two. Okay. So we can say that there's a dipole moment going in this direction over here and a dipole moment going in this direction over here. Okay. The thing is, I can't break this molecule into a half where there's positives and negatives, right? A half where there is a positives on one half of it and negatives on the other. So because of symmetry, carbon dioxide is nonpolar. It's got polar bonds, but it doesn't have a molecular geometry that allows the molecule to have the positives on one side, negatives on the other. Okay. You'll recall that water was oxygen with two hydrogens on the side, but water was bent. And so because water was bent, you can basically make a line right here where the oxygen was on top of the line, the hydrogens were below. And we got a dipole moment in the whole molecule. This one, if it was bent, it would be polar. But since it's not bent, the negatives on this side offset the negatives on the opposite side. So those are nonpolar molecules. Here's a couple other. This is an example of two nonpolar. Well, one's a nonpolar molecule. The other one's a polar molecule. The one on the left here is CCl4. The one on the right is CH2Cl2. Okay, so the difference between this one and this one is that two of these chlorines have been substituted with hydrogens over here. And we have a polar molecule here and a nonpolar molecule here. Okay. Why isn't this molecule polar? Well, because, well, it's got 4 polar bonds. Between carbon and chlorine, there's enough of a difference we can say there's a polar bond or a dipole moment. And you can see it's right here. We have a dipole moment here, here, there. So there are 4 dipole moments on this molecule. But well, there's no way we can cut this molecule to put the positives and negatives just on one side. So this chlorine right here has a negative on it, but so does this one, so does this one, so does this one. So all the chlorines are on the outside, and the positive carbon is on the inside, slightly positive. Right? So we can separate the inside from the outside, but that doesn't make it polar. Right? You have to be able to put a line through the molecule and separate the pluses from the minus. Now we can do that with CH2Cl2 because carbon has an electronegativity of 2.1. Carbon's 2.5. Hydrogen's 2.1. This one's hydrogen's 2.1. It's kind of almost nonpolar, but we'll call it slightly polar. If it was polar, these guys would have the partial positive on this side. The chlorines are more polar, just like over here. The chlorines are more electronegative than the carbon, so there's a partial negative here, there's a partial negative here. So we can split the molecule here, and one side all the positives, the other side all the negatives. It's a polar molecule. Okay, and so what effect does that have on the molecules? Well, it goes back to the whole why don't water and oil mix? Because water is polar and oil is nonpolar. And by the way, those are not the only compounds that are polar and nonpolar. There's a whole bunch of them, but that's the most common one. Polar molecules mix with other polar molecules because their dipoles attract each other. And nonpolar molecules mix with other nonpolar molecules. Now, since water is polar, right here, polar substances are called hydrophilic. So if there's something else like let's say alcohol or other substances that dissolve readily in water, acetone. There's a whole bunch of chemicals that dissolve with water. You can call them polar, or you can call them hydrophilic. And hydrophilic is a term that just kind of tells you, well, does it dissolve in water? Non-polar substances, since they don't dissolve with water, are called hydrophobic because phobic means to fear, right? So it's fearing water. Phil means to love, so these are loving water. Okay, so there's a couple other terms. And why are they that way? Well, okay, here's an example. Let's say that we have these particles here with the plus and minus are polar molecules. The ones without the plus and minus are nonpolar, right? So these could be water with a plus and minus. And the ones without anything on there could be oil molecules. Now, generally, oil molecules are much bigger, but this has the same effect. And so what happens is all the polar molecules are attracted to each other, right? The negatives of one polar molecule attract the positive of another one here or that one there. They all start attracting each other. And so out of all the tiny particles all over here, all the polar molecules start gravitating toward each other. And when they gravitate toward each other, they kind of separate out. Okay, it's kind of like a bunch of, let's say a bunch of students, and there's certain students that all know each other and they want to hang out with each other, so they go ahead and do. And so now you end up with 2 groups: the ones that want to hang out with each other, and the other ones that I don't want to say they want to hang out with each other, but they don't care. They get kind of pushed out. So we get a layer of hydrophilic polar water molecules and a layer of hydrophobic or nonpolar oil molecules. Okay, so that's how it works, and it works with a whole bunch of other stuff. Dirt is nonpolar. Okay. And later on, second semester, we'll talk about how soap works and how soap kind of brings the two together so that you can go ahead and get that dirt off the water. Dirt off your hands by using water. So let's talk about doing this worksheet. Okay, so one thing to point out is I'm not going to test you or quiz you on doing the polar molecules, just because we don't know enough math. You got to be able to do three-dimensional calculations of vectors, and that's something most people don't learn till they're at least in uh, physics and what do you call it? Calculus, right? So what I'm going to do is just make sure that we know how to calculate polar bonds. Okay, and so here's the worksheet that you're going to be working on to calculate polar bonds. And you're going to see that there is a column that says pairs of atoms. So you're going to have a whole bunch of pairs of atoms here, and you're going to decide eventually what type of bonds are formed between the atoms. You got three choices: polar covalent, non-polar covalent, and ionic. Okay. And so what you're going to do is this. You're going to look up the electronegativity for each atom. There's a chart in your book in chapter 9, section 5, which you just read. And you're going to look up the electronegativities, write them down. So here, the pair of atoms are hydrogen and chlorine. You're going to write hydrogen and chlorine. You're going to look it up. And you're going to write down their electronegativities. By the way, just to let you know, your hydrogen and chlorine might not match, in the book, might not match this one. There are several electronegativity tables that are floating around out there. I don't think anybody's decided which one's the correct numbers, but what we care about is the differences. So they should be pretty close in differences. So even if these numbers don't match yours, they're probably pretty close, and the electronegativity differences are pretty close too. So this the next chart here, the next column will be the electronegativity difference. You just take the difference between these two. So 3.16 minus 2.10 is 1.06. If there's electronegativity difference between 1.06, what is that? Is that polar covalent, non-polar covalent, or ionic? And remember, basically, the way we've set it up was 0.5 or less, we'll go with non-polar covalent. Well, let's say less than 0.5. We'll make the 0.5 to be polar, slightly. The borderlines are really kind of tough. So if it's less than 0.5, it's non-polar covalent. If the difference is greater than 0.5 and less than 2.0, it is polar covalent. And if the differences are greater than 2.0, then we'll call it ionic. And this is where you'll write it down. So you'll get the differences here, and then you'll write them down here. Okay. And then what you need to do in this one is write down whether the first and second elements are metals or nonmetals. Because remember, we had kind of a basic rule. Ionic compounds are made up of metal and a nonmetal. Molecular compounds are made up of nonmetal and nonmetal, like this one. This one is a nonmetal. And so therefore, we wouldn't expect it to be ionic. We would expect it to be covalent bond between the two. And it is, but it's polar covalent. Turns out that rule is kind of a general rule, and you'll see some pairings here where there's metals with higher electronegativities along with nonmetals that are lower electronegativities that make a metal, and certain metals and nonmetals bonding, even though the rule is metal nonmetal is an ionic bond, it'll make them maybe polar covalent, okay, instead of ionic. So you want to kind of check. We can kind of see, well, metal nonmetal is metal nonmetal always ionic? It almost always is, but we can see if our rule here follows this information that we're getting, we'll call empirically, right, through experimentation. You do the same with the others, K and F, right? Find their electronegativities on the chart in section 9.5 in your book, get the difference, decide whether it's non-polar covalent, polar covalent, or ionic, and then write down whether K is a metal or non-metal, and F is a metal or non-metal. Okay. Do it for all those down here. Okay. Then answer the questions at the bottom, which, are basically talking about the dipole moment between two elements. Which bonds are the most polar? Which ones are the least polar? Okay, and that's all. This is actually a pretty easy worksheet, so hopefully it won't be too hard. Hopefully, I have Kami open here. You can annotate it with Kami, or you can write it with your by hand and then scan it with CamScanner or something like that. Okay. All right. I hope this was helpful.